Hey, algebra, new unit. Whoops. Okay, new unit. We're on number 3. Number 3 starts back into linear equations, but first we have to learn about sequences and then functions. Super important in your development of your algebra skills, but things are going to get a little bit more difficult. So you're going to have to focus in on the lesson videos and make sure you make notes to ask questions if there's something you don't understand. So let's get into it. First of all, Mrs. Rosenblatt gave her students what she thought was a very simple task. What is the next number in the sequence 2, 4, 6, 8? Cody, I am thinking of a +2 pattern, so it continues 10, 12, 14, 16. Allie, I am thinking of a repeating pattern, so it continues 2, 4, 6, 8, 2, 4, 6, 8. Surrey, I am thinking of the units, digits, and the multiples of 2, so it continues 2, 4, 6, 8, 0, not 10, 2, 4, 6, 8. What she means is the units digit, like, we're going to go 2, 4, 6, 8, 10, that's the units digit, 12, 14, 16, 18. So the units digit, just the digit in the ones space. Are each of these valid responses? Well, yes, they all work, right? Each one follows a pattern. So what is the 100th number in the sequence in Cody's scenario, in Allie's scenario, and in Surrey's scenario? So this takes a little bit more work. If we look at Cody, we've got 2, 4, 6, 8, 10, 12, 14, 16. That's the 8th term. 18, 20 is the 10th term. So for Cody, the 10th term is 20. If we're looking at the 100th term, that would be 200 for Cody. Allie, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 would be 9, the 4. So wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it's this one repeated over and over again. Okay, we're going to circle and hit that one every 20th time, which 5 times gets us to 100. And then Surrey's, the digits and multiples. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 0 every time it circles back around. So here is sort of what we're getting at for the day. What is an expression in terms of n for the nth number in the sequence of Cody's scenario? Here's where I would ask you, what does this mean? Nth term. Well, if I look at Cody's scenario, I have 2, 4, 6, 8, 10, 12, etc. This is the first term, the second term, the third term, the fourth term, etc. So if I were to write an expression for this, it could be just plain old 2n. So when n equals 2, 2 times 2 equals 4. When n equals 5, 2 times 5 equals 10. It works out. So that would be one expression that would work. Okay, that's when we start out with n equals 1. If we start out with n equals 0, so sorry, this starts out with n equals 1. If we start out with n equals 0, it's more like 2 times n plus 1 if we start out with n equals 0. So n equals 0, 0 plus 1 is 1, so the first term is 2. Let's do that. Let's change that color. So if we have n equals 0, we have 2 times 0 plus 1, so 2 times 1 is 2. That would be for purple, n equals 0, n equals 1, n equals 2. We're going to talk about where we start, either with the first term or the 0th term, as our lessons continue. But today we're just playing around. We're learning how to write some sequences, which is sometimes sort of difficult. All right, to talk about that a little bit further, the first time we talked about Cody's expression, we said the expression was 2n when we start with n equals 1. And then we talked about it being 2 times n plus 1 if n equals 0. Is one of them more correct than the other? Well, nope, it actually isn't. Sometimes we can start with n equals 1, sometimes we can start with n equals 0. You just have to tell me which you started with. That's really important. You sort of set your base rules, right? We will almost always start with n equals 1, and we'll keep on talking about it. But it just makes more sense to start with the first term rather than to start with the 0th term, right? So it just makes better sense for, it's very natural to start with n equals 1. There are some, oh gosh, I wrote 0. There are some cases when we'd want to start with n equals 0, but we're just going to stick with n equals 1 for as much as possible. Cool? Cool. All right, let's try an example. Jerry has thought of a pattern that shows powers of 2. Here are the first 6 numbers of Jerry's sequence. Write an expression for the nth term of Jerry's sequence. Well, we sort of have to figure out what the pattern is, right? If I look at it, I'm going to have a term number and then the term. So when the term number is 1, my term is 1. Term number is 1, my term is 1. When my term number is 2, my term is 2. The second term in my sequence is 2. The third number in my sequence is 4. Third number is 4. The fourth number is 8. I'm going to run out of colors. The fifth number is 16. And the sixth number is 32. I can rewrite that table into something with sequences that will hopefully, that this will lead to this making more sense. We're going to hope. We can also label sequences as A1, A2, A sub 3. I said sub that time, that's correct. A sub 4, A sub 5, and A sub 6. And then our term is 1, 2, 4, 8, 16, and 32. And we can also put that in what's called function notation, which we will get into further. F of 1, the function evaluated at 2, f of 3. I'm saying them in both ways because they're both valid. The function evaluated at 4, the function evaluated at 5, or the function evaluated at 6, which is f of 6. I can continue that on to do a sub n. I can continue this on to say f of n. All right? You guys should be familiar with that a sub n notation. The f of n notation is also something that you may or may not be familiar with, but we're definitely learning about it this unit. It's called a function notation. This is called a sub n because it's a sub, it's written lower, a sub 6, it's the sixth term. This is f of 6, f of n. So it's the function evaluated at 6, the function evaluated at n. We still didn't figure out his expression though, did we? Let's just do that. 1, 2, 4, 8, 16, 32. I know that 2 raised to the 0 power is 1. First power, second power, third power, fourth power, and fifth power. Okay, let's see our pattern here. If I see all of these are the same, right? And then 0, 1, 2, 3, 4, 5. If we're talking n equals 1, our first term, we're going to say that is 2 to the n minus 1. So this one would be 2 to the 1 minus 1, which is 2 to the 0. For n equals 2, I get 2 to the 2 minus 1, which is 2 to the first power. I get 2 to the 3 minus 1, which is 2 squared, n equals 4, 2 to the 4 minus 1, 2 cubed, n equals 5. You get the pattern, I'm sure. 5 minus 1, 2 to the 4th, 2 to the 6 minus 1, which is 2 to the 5th. So I have my expression, which is all the way up here, 2 to the n minus 1, where I have to say my first term starts with 1. Okay, so the expression is 2 to the n minus 1, starting with n equals 1. All right, let's consider the sequence that follows a plus 3 pattern. Okay, 4, 7, 10, 13, and 16. Write a formula for the sequence using both the a sub n notation and the f of n notation. Now I want to call out again, this right here is called function notation. It is not f times n because it's parentheses. It's a function, which is an equation evaluated at the value n. Okay, so we are not multiplying here at all. It's just a name. I've always just said that function notation is a name. So when we talk about the function f of n, we're just going to say it's like calling an equation or a special expression frank. Okay, it's just naming it. It's frank. All right. We're going to have lots of different function names, but f of n is the most common name for a function. It's like a formula or a different way to name an expression. So write a formula for the sequence using both the a sub n notation and the f of n notation. So if we're doing a plus 3 pattern, we want for n equals 1, is where we're going to start out. To get to 4, I really want it to be, it's a plus 3 pattern, so I'm going to start out with a 3, multiplying that by n. So if n is 1, that's 3, so to get to 4 I have to do that. And I always just test out a few when I do that. So a sub 1 is going to be 3 times 1 plus 1 equals 4. A sub 2 is 3 times 2, which is 6, plus 1 is 7. It seems to be working. I always test them out. I don't know why. And then we can do the function notation. Is 3n plus 1. Both of them start with n equals 1. Does the formula f of n equals 3 times n minus 1 plus 4 generate the same sequence? I don't know. Let's look. So I've got, it's a plus 3 if n equals 1. 1 minus 1. Wait. Yep. Plus 4 gives me 0. Plus 4 equals 4. That's for n equals 1. N equals 2. I get 3 times 2 minus 1, which is 3, plus 4 is 7. Seems to work. N equals 3, just triple checking. 3 minus 1 is 2, so that's 6, plus 4 is 10. So yeah, it seems to work. Why might some people prefer this formula? I don't know. It gives us, I like that it gives us this as the answer for the first one. That goes away, we know that it's 4. And then if we look at this, I get a 3 plus 4. So it's like my plus 3. And then if I look at this one, I get 6 plus 4. So it's like a plus 3 pattern. So it makes sense. You can get creative with your with your expressions. Graph the terms of the sequence as ordered pairs n, comma, f of n. So when n equals 1, we had 4. When n equals 2, we had 7. N equals 3, 10. N equals 4, 13. N equals 5, 16. Let's go ahead and graph that. So I go over 1 up 4. Oh, that's huge. Over 1 up 4. Oops, not quite on the dot. Over 2 up 7. 5, 6, 7. 3, 10. 4, 13. Oh, 10's not right. 13. And 16. There we go. What do you notice about the graph? In essence, we cannot connect the dots because it's not a linear function. Every time we input something, so we input a 1, we get a 4. We input a 2, we get a 7. So it's not a line per se, but it does form a pattern that I could connect a line through. But we shouldn't. But it is linear. Oops. We should say that it forms a linear pattern. Refer back to the sequence from the opening exercise. When Mrs. Rosenblatt was asked for the next number in the sequence, 2, 4, 6, 8, she said 17. The class responded, 17. Yes, using that fancy-dancy formula, she got 17 for the next term. Does her formula actually produce the numbers 2, 4, 6, and 8? Let's check. I'm going to try f of 1, 7 over 24. I get 1 minus 1, so that cancels. Minus 7 over 4, 1 minus 1. Oh, this should be to the 4th power, so that cancels. Plus 77 over 24, 1 minus 1 squared. Plus 1/4, 1 minus 1, plus 2. So that one worked, right? Let's check it for f of 2. I'm not looking forward to this, are you? 7 over 24. 2 minus 1 is 1 to the 4th power. Minus 7 over 4. 2 minus 1 to the 3rd power. 77 over 24. 2 minus 1 squared. 1/4. 2 minus 1 plus 2. If we do 7 over 24 minus 7 over 4 plus 77 over 24, plus 1/4 plus 2, we do in fact get 4. Amazing. Okay, whoops. So if we evaluate the function at 3, we are going to get 6. And if we evaluate the function at 4, we will in fact get 8. That's crazy, right? What is the 100th term in Mrs. Rosenblatt's sequence? So we're going to evaluate the function at 100. Okay, hold on, I'm going to put up my calculator. Phew. 2, 6, 3, 5, 0, 8, 3, 2. Okay, big number. Consider a sequence that follows a -5 pattern. So we're getting smaller and smaller and smaller. Write a formula for the nth term of the sequence. Be sure to specify what value of n your formula starts with. So if we are doing a -5, we need to actually start with our beginning. And we're going to subtract 5 each time. So if I write, so for my first term, I'm going to subtract 5. For my second term, I need to subtract 5 twice. For my third term, I'm going to have to subtract 5 3 times. Fourth term, 5 4 times, right? So I always test out a few. F of 1 is 30. Oh, I made a mistake. We have to start with 35 if we're subtracting 5 each time, right? Okay. Oops. So this is why I always check them. I'm going to start with 1 more than the beginning, and I'm going to subtract 5. And then for my second term, 35 minus 5 times 2, which is 25. Third term, 35 minus 5 times 3, which is 20. It works. Using the formula, find the 20th term. So f of 20 is 35 minus 5 times 20, which is 35 minus 100, which is negative 65. So graph the sequence. Let's see, I had first term was 30, second term 25, third term 20, fourth term 15. So let's go ahead and graph it. I'm going to go over 1, up 30. This one's going to be a little rough. 2, 25. 3, 20. Oh, I made a mistake already. 225, 320, 4, 15, and we could keep going, right? Those are all the ones that I have to. And what do we notice? The pattern is again linear. Okay, we can't actually connect the dots, but we can show that the pattern is linear. Right. Consider a sequence that follows a times 5 pattern. Okay, now we're multiplying each time. It's really interesting when we start with a 5 times pattern. We're going to have a 5 raised to a power. Now if our first term is 1, everything raised to a power of 0 equals 1. A million raised to a power of 0 equals 1. Okay, so I can raise it 5 raised to a power of 0, but for my first term, n equals 1. So that would be 1 minus 1 is 0. My second term, I would have 2 minus 1, which is 1. 5 raised to the first power is 5. Etc., etc. So I wrote a sequence. If we're doing a times 5 pattern, that's why I get that there. My first term is 1, so I need the beginning to be raised to a 0 power. To get 5 raised to the 0 is 1. Let's test it. 5 of 1 is 1 minus 1. F2 is 5 to the 2 minus 1, which is 5 to the 1, which is 5. F3, 5 to the 3 minus 1, which is 5 squared, which is 25, etc. It works. Let's find the 10th term. It's 5 to the 9th power, which I just typed it out, is 1953125. So that is f of 10. Cool, let's graph them. You have it in front of you. My first term is 1, so over 1, up 1, oh my, that's near impossible. Over 1, up 1. Over 2, up 5. I love this graph they've given us. Over 3, up 25. 4 was 125. 5 is bigger and bigger. Okay. Now this one we cannot say is linear, and we'll get into why in a future lesson. Ooh, patterns. All right, square numbers. We've got 1, 4, 9, 16. If you notice, I add sort of a length and width to each one. That takes me to the next one. Right? Right, the nth term of the sequence, we sort of need an equation first, right? Well, if we have f of n equals, if n is 1, 1 squared is 1. If n is 2, 2 squared is 4. If n is 3, 3 squared is 9. If n is 4, 4 squared is 16. So that's what we're going for. I've got n squared starting with n equals 1. So if I were to find the 50th term, 50 squared, which is an easier one to do, 2,500, that's a lot of dots. And if we graphed those, we would get 1, 1, 2, 4, 3, 9, 4, oh, 9 doesn't look very good. Still not. 4, 16, 5, 25, etc. And this one we can also say is not linear, and we'll get into why in a future lesson. So a standard letter-sized piece of paper has a length and width of 8.5 by 11 inches. Find the area of one piece of paper. Length times width. 8.5 times 11 is 93.5 inches squared. Okay, that is 8.5 times 11. If the paper were folded completely in half, what would be the area of the resulting rectangle? We're going to assume that, well, if this is 8.5 by 11, if we fold it in half, we're going to have 8.5 times 5.5. So the area would be 8.5 times 5.5, which is 46.75 inches squared. Write a formula for the sequence to determine the area of the paper after n folds. Oof. So we need to divide by 2. Let's see. I don't quite have it yet, but we can work on it. If I take the first area and divide by the second area, I get 2. So 93.5 is the beginning. If I divide it by 2, I get the second area. So I'd like to try to work with this pattern. Now if we fold that in half again, we would get 8.5 times 2.75. 8.5 times 2.75 is 23.375. So I'm going to see if that equals that. It does. 46.75 divided by 2 is 23.375. That helps me figure it out. So from the first area, I divided by 2 and I got the second area. And then I divided by 2 and I got the third area. So what I really need to do is take my original area and divide it by 2 to the n. So my original area was 93.5, and I'm dividing it by 2 to the n. So for n equals 1, that's my first fold. N equals 2 is my second fold. N equals 3 is my third fold. So after 7 folds, I would have 93.5 divided by 2 to the 7th power. That equals 73046.875 inches squared. It's an itty bitty 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 area. And that's it. That was our fun for the end. Sequence, an ordered list of elements. Okay, explicit formulas are so hard to come up with, but with practice, they are easier. Practice equals easier. Find the first term by substituting 1 into the formula. That means that n is going to be 1 unless we specify otherwise. Good job. That was a long one.